So we will, do you want me to cover any particular example that in the class which might be of interest to you? Otherwise, I will choose on my own and then we'll discuss that.
Sir, take the problem related to our meteorological data.
Okay, you mean this one? Did we cover this time series forecasting with weather prediction? I think we did, right?
Yes.
Okay. Okay, so yeah, I think we can take variational autoencoders. So you can go and see this autoencoder monsoon paper by Momita Saha and Ravi Nanjundaya. Okay, so she has basically used autoencoders for predicting the monsoon over. I mean, this is, I think, a follow paper. Even this is fine. Like over homogeneous regions of India. So, can anybody tell what is autoencoder? We already covered in the class. Yes, no. So, autoencoder is nothing but it's a neural network which has got the same inputs and same outputs. Okay, like your input variable and your output variable is same. So, and why you need an autoencoder is because, so what you can do is, so you can see that there are these latent representations, right? These layers in between. You can take these layers, and using these layers you can you can use these layers as some kind of refined predictors. Okay, so let's say you just give an input as x, maybe rainfall as an input and rainfall as a target. So these numbers that you will get like in between of these layers, this is these are like better predictors of that you can use in your problem. So in this like this paper, she has used autoencoders, and you can see her previous papers also. So what they basically do is they take this entire globe and divide it into boxes of size, I think 10 degrees by 10 degrees, and take the area average of these boxes. Now from the area averaged area, so you have time series for every box. So then they use a method to find out. So for okay, so here it is shown central Indian summer monsoon. So what she does is that she finds out the what regions on the globe they have a good, for example, correlation with the with sea level pressure. Okay, so there are these sea level pressure regions that she identifies. Okay, S1 to S5. And what are those? So what is the kind of correlation that is? So these are the regions which have good correlation with the central Indian summer monsoon rainfall. So after identifying these predictors, then she applies the autoencoder framework. So using the autoencoders, she gets the better better or latent representation of the predictors. So the predictors that she has used here are sea surface temperature, sea level pressure, U wind, and geopotential height. Now with these latent or with these better predictors, she uses an ensemble of regression trees prediction model to predict the summer monsoon rainfall over India. and this model performs reasonably well. So you can see that the prediction by sea level pressure, prediction by U wind, prediction by SLP plus U wind is star, and the box is the actual prediction. So this is for the central India summer monsoon rainfall. This is for the northeast India summer monsoon rainfall, and this is for northwest India, the south peninsular India, and the actual versus predicted. Okay, so this study uses autoencoders. I think enough of like an introduction to why we should use it. Why we should study autoencoders. So we will see the code. Yeah. So these are conditional variational autoencoders trained on MNIST digits. So as we have seen autoencoders, there is something known as conditional, or first of all, you need to understand what is a variational autoencoder. Okay. So variational autoencoders. So what you basically have is you have this latent representation, right? So autoencoder basically, so when anybody talks about an autoencoder, what you are trying to do is you are trying to do dimensionality reduction. You can do with principal component analysis also. For example, here you can see this is your encoder, this is your encoder, this is your decoder. If you have the same X as input and same X as output, what you're getting as encoded data is like kind of a compressed version of your input data, right? Which is also called as the latent space or the encoded space. So in autoencoders, like you simply have the same input and same output, and that's your autoencoders, and your error is measured by some kind of loss function between X and X hat. So just a second. Okay, so then we have something known as variational autoencoders, and so autoencoders are encoder decoder architectures, can be trained by gradient descent, and in variational autoencoders, like instead of just having the inputs, so you can think of it as autoencoder whose training is regularized. So you basically have the distributions so you have a mean and a standard deviation instead of just the latent representation. So instead of encoding an input as a single point, we encode it as a distribution over the latent space. So the model is trained as first the input is encoded as distribution. So the way you will make a distribution is you will have a mean and a standard deviation, like that. You can choose any method for encoding the information as a distribution, and then a point from the latent space is sampled from that distribution. That the sample point is decoded and reconstruction error can be then computed. So then finally the reconstruction error is back propagated through the network. So in a simple autoencoder, you have an input X, you have a output again which is X, or you can say D of Z, which is a reconstruction of this input, and you have a latent representation. So you have encoding and you have decoding. In variational autoencoders, you have an input X. Now the encoding it leads you to a latent distribution. You sample from this latent distribution. Okay, so you sample some number. So for example, from some normal distribution, you just extract some number, and then the decoding happens, which will lead you to the same reconstructed X. So in practice, encoded distributions are chosen to be normal so that the encoder can be trained to return the mean and the covariance metrics that describe these Gaussians. So the reason why an input is encoded as a distribution with some variance instead of single point is that it makes possible to express very naturally the latent space regularization. And the distributions returned by the encoder are enforced to be close to a standard normal distribution. So you can see here an example of a variational autoencoder. So you have an input X, you have a neural network encoder, which returns a mu and a sigma, which is the mean and the standard deviation. Now you sample some numbers from this distribution. So like a normal distribution, which is represented by the this mean and the standard deviation. And with these sample points, you try to reconstruct this X again. So that is your later variational autoencoder. And the loss function that is minimized when training a variational autoencoder is composed of a reconstruction term on the final layer that tends to make the encoding decoding scheme as performant as possible, and a regularization term that tends to regularize the organization of the latent space by making the distributions returned by the encoder close to standard normal distribution. So the regularization term is expressed as Kullback-Leibler divergence, which is also known as the KL divergence, between the return distribution and the standard Gaussian, and will be further justified in the And so what are the intuitions about this regularization term? So the regularity that is expected from the latent space in order to make generative process possible can be expressed through two main properties. One is continuity. So two close points in the latent space should not give two completely different contents, and completeness. So which is for a chosen distribution, a point sampled from the latent space should give meaningful content once decoded. So herein they are giving an example of irregular latent space. So these are 2 points, close points in the latent space that are not similar once decoded. So the close points, when they are decoded, they should be similar, right? When you apply a decoder to those close points in the latent space, they should be similar to each other. So so this is so point from the latent space is like meaningless once decoded. So that is a irregular latent space. Now a latent regular space is latent space where points that are close in the latent space are similar when decoded. So for example, you decode this red, you get this kind of a triangle, right? You decode this orange, you get this triangle. So you decode this one, you get a similar shape here. So these points are near to each other, they are getting decoded in a similar manner. So you see this is far and this one is far, the blue is far, so it's decoded like when you decode this, it's like this is like cryptography. You encrypt and you decrypt. So you get something different when these points are far away from each other. So the only fact that variational autoencoders encode inputs as distributions instead of simple points is not sufficient to ensure continuity and completeness. Without a well-defined regularization term, the model can learn in order to minimize its reconstruction error, to ignore the fact that distributions are returned and behave almost like classical autoencoders, basically which would lead to overfitting. And to do so, the encoder can either return distributions with tiny variances or return distributions with very different means. So in both the cases, distributions are used the wrong way, and continuity or completeness is not satisfied. So we have to regularize both the covariance matrix and the mean of the distributions returned by the autoencoder. And in practice, this regularization can be done by enforcing distributions to be close to a standard normal distribution. And this way, we require the covariance matrices to be close to the identity, preventing punctual distributions, and the mean to be close to zero, preventing encoded distributions to be far apart from each other. So you can see what happens without regularization. So we have a distribution here, okay, which leads to when you decode this, it gives you this triangle. You decode this distribution, gives you this square, and like you are just randomly getting something. This is the purple thing, and you have this distribution. And whereas when you regularize these distributions, we get something that we want. So you have like you have these distributions which are the actual numbers are close to each other, and you get some kind of meaningful, so you have a completeness, right? So the entire space is kind of being covered by the distributions, and you have a completeness in this case. So with the regularization term, we prevent the model to encode data far apart in the latent space, and encourage as much possible return distributions to overlap, satisfying this way the expected continuity and completeness conditions. Naturally, as far for any regularization term, this comes at a price of higher reconstruction error on the training data. So the trade-off between reconstruction error and KL divergence can, however, be adjusted, and we will see in the next section how the expression of balance naturally emerge from the formal definition. So, and to we can observe that continuity and completeness obtained with regularization tend to create a gradient over the information encoded in the latent space. So for example, a point of the latent space that would be halfway between the means of two encoded distributions coming from different training data should be decoded in something that is somewhere between the data that gave the first distribution and the data that gave the second distribution. For example, this point. So this came halfway between the means of two encoded distributions. So this should be represented by between the data that gave the first distribution and between the data that gave the second distribution. In fact, this is coming from in between all these three distributions. So these are some mathematical details of variational autoencoders, and so I think you got the basic idea of these variational autoencoders. Like it's nothing but like you have a mean and a variance, a mean and a standard deviation, and then you are sampling the latent distribution from the mean and the standard deviation. Whenever you think about variational autoencoders, like this this image that we saw, yeah, like you should just like this should be, you should remember this diagram. So you have mean and standard deviation, you sample from this distribution, and then you decode it. So we will run this example for variational autoencoders, and these are convolutional variational autoencoders trained on MNIST digits. So rather than just doing simple simple scalar weights, if you do if you are having your inputs as 2D and your filters are also 2D and you are doing convolution, that becomes a convolutional variational autoencoders. So we will import these libraries, and we'll make this class sampling class. So this is coming from layers. So this layers from this layers class, in which is defined in tensorflow.keras. So this basically uses the mean and the log of variance, right, to sample to get a sample z. So you can see this as we define a single function call here. So this call basically takes in these inputs, and this input is, I think, a list which is consisting of mean and the log of variance. So then you create a TensorFlow variable called batch, and its shape is equal to the shape of the mean, and you create another one which is dim. So its shape is also equal to the shape of the mean, and then you create an epsilon. So the epsilon is from TensorFlow Keras, from the random normal distribution. So your mean and the standard deviation and the dimension. So whatever the size of these input is, so similar to that size, you create this epsilon, and you return mean plus e to the power, so 0.5 into log of variance into epsilon. So this is what we are returning. Now we will build the autoencoder, build the encoder. So let's say our latent dimension is 2. What do we mean by latent dimension? That this dimension, this is 2. Here we can see the latent dimension is 3, right? And the encoder inputs, so they are so we are having a keras dot input. So keras dot input, and we are having an image of size 28 by 28, and then these encoder inputs, so we pass them through a convolution layer having 32 filters, each filter of size of kernel size 3 cross 3, and we have the activation function as relu. Number of strides is 2, padding is same. So you pass it through. So you see the encoder inputs is passed through this convolution layer, and then you get this x, and then again you pass this x through this another convolution layer. You flatten this out, and then we have a dense layer consisting of 16 neurons. Activation is again relu, and then you have this the mean, what we call as the mean. So that is, so you have another dense layer whose dimension is this latent dimension, and the name of this layer is z mean, and you have another log of variance layer, so which has a dimension again which is 2, and its name is z log variance. These two then you pass to this sampling layer, okay, and you say z equal to sampling z mean comma z log z log variance. So this is the input list that you pass to this sampling function, and with this z, so you create the encoder. So in the encoder you create the model, so which has the encoder inputs, and what you get in the output is z mean, z log variance, and z, and the name of this is encoder. So you can see here we had this 28 by 28 by 1, then we got we have these 32 filters, so we have corresponding 32 different channels here, and the size will be 14 cross 14 because the stride is 2. Then again you see we have another convolution with stride as 2, so the size will again decrease by 2, so this becomes 7 cross 7, and you have 64 filters. Sorry. So we have 64 channels here, and then we flatten it out. So flattening basically means that 7 cross 7 cross 64, we have 3136 nodes, and then we have a dense layer which has got 16 nodes, and then we have a z mean and z variance and a sampling layer. So z mean and z variance depend on the x, so whatever is coming out from dense, and the sampling depends on z mean and z log variance. Now we will build the decoder. So in the decoder we will have the input as the we'll use keras dot input, and the shape is the latent dimension. So the latent dimension is 2, and now we will make a dense layer of size, so with this many number of filters, 7 cross 7 cross 64. So you can see here like as you made the encoder, in a similar way you create a decoder, so of size 7 cross 7 cross 64 or 3136, and then you, after this dense layer, you reshape it to 7 cross 7 cross 64, and then you use the con 2D transpose. So con 2D transpose, this will this will do a inverse convolution or a deconvolution. So as we can see here, transposed convolution layer, sometimes called deconvolution, and the need for transposed convolution generally arises from the desire to use a transformation going in the opposite direction of a normal convolution. That is, from something that has the shape of the output of same convolution, some convolution, to something that has the shape of its input, while maintaining a connectivity pattern that is compatible with the said convolution. So you have a con 2D transpose, 64 filters, size of each filter is 3 cross 3. Activation is relu. Now you see here we use stride as 2. So you use a stride as 2, padding same. This will basically make the size double. Okay. So 7 cross 7 will become 14 cross 14. Okay. And then you do the same thing again. So 14 cross 14 now will become 28 cross 28. Okay. So then, so these are the decoder. So then the decoder outputs is equal to layers.con 2D transpose. So you just have a single, so you just have a single filter of size 3 cross 3, and padding is same. Okay, activation is sigmoid. So this will basically not change the size, because stride only changes the size if your padding is same. And then you have your you build your model. This is the decoder model with the latent inputs as input and the decoder outputs. So this is the output, and the name is decoder. So you can see here from the summary. So you see here we have used one filter. So the number of channels eventually in the output becomes 1. Okay. Now we can define the variational autoencoder as a model with a custom train step. So this is the class of the variational autoencoder model, and it is built on the keras.model class. So in the constructor, we will basically first run the constructor of the parent class, that is keras.model. So super function does that. Super, we have to give the name of our child class, comma self dot init, and whatever arguments we are taking. So you can see that while defining the variational autoencoder, we need to give the encoder and the decoder. And then we have total loss tracker, which is equal to keras.metrics.mean, name equal to total loss. And we have a reconstruction loss tracker. So reconstruction loss tracker, we'll see this. This is mostly the how your reconstructed output is as compared to the input. And then we have the KL divergence loss tracker. So this is the mean, and its name is KL loss. So then we will create so this is a metrics function. It's a property of this class, so that's why we have decorated it with this @ property. We've already seen what does it mean by a decorator. So it's like property is a function and its argument is metrics. And then we'll see, okay, so this is the train step. So in the train step, you get the data, and we use a tf.gradient tape as tape, and we will pass the data to the encoder. And what will it give us? It will give us the z mean, z log variance, and z. Now z is our latent output from the encoder. That latent output we will pass to the decoder, right? And we will get the reconstruction. Now this reconstruction, from this reconstruction, we'll compute the reconstruction loss. So which is tf.reduce mean, and you basically compute a binary cross entropy loss between data, which is the input, and the reconstruction, which gives you the reconstruction loss. And then we have KL loss here, so which is defined. So it's like you can see from its formula, and so you then use a TF dot reduce mean, and you find out the total loss. So this is KL loss is like how different are the distributions of your input and your output. So that is the KL divergence loss or Kullback Leibler divergence loss. And then we have the optimizer. So where is the optimizer? I think while defining, we will create the optimizer, which comes in these KW args. So then we apply the gradients to the trainable weights, and then we so the total loss tracker, we update the state, and the reconstruction loss tracker, and for the KL loss tracker, and we will return the loss, the reconstruction loss, and the KL loss. So this was the variational autoencoder class. So then next we will see, okay, we will load this MNIST data, which is from the keras.datasets.mnist, and the what are our MNIST digits. So these are our MNIST digits. So let us see what is there in this. Okay, so you can see that we have 70,000 images of size 28 cross 28. Okay, and 28 cross 28 cross 1. So you remember, right? We don't have an input and output like a labeled data in an autoencoder. So we just have a single data set, right? That's and similarly in variational autoencoders. So since this is an image data set, we have normalized the data or divided by 255, and here we will basically create the variational autoencoder with an encoder and a decoder. So you see, this is the variational autoencoder, and we'll say VAE dot compile optimizer equal to keras dot optimizers dot Adam. So with the Adam optimizer, we will compile it, and we will say variational autoencoder dot fit. So you just have to say VAE dot fit. So if you create this function train step metrics and init, you just have to say VAE dot fit MNIST digits. So this is your data. Okay, so this is your data, and we'll run this for 30 epochs and a batch size of 128. So let us see this for some time. This will take some time. Any questions? Am I audible?
Yes. Yes, sir.
Okay. Am I not using the GPU? Oh, I'm sorry. I was not using the GPU, so this will be faster now. So here we will plot the latent space. Let us see how it looks like. So you can see, so this is Z0 and this is Z1. So they are basically you sample the, this is the Z sample, and you find the X decoded. So you, from the decoder, you take the Z sample, and you then predict for different combination of Z0 and Z1, basically mu and standard deviation. What is the corresponding decoded image? Okay, so VAE dot decoder dot predict. This will give us X decoded, and X decoded we basically reshape as digit size, comma digit size. It will be 28 cross 28 cross 1. We are just removing the final, that the third dimension, which is redundant. So you can see numbers which are closer to each other. They are represented so by the in the latent space in the distribution, which are near to each other, and display how the latent space clusters are with different uh, digit classes. So you can see that in this, with this Z0 and Z1, so you can see that this corresponds to a particular number, right? Green, which should be either 6 or 7. And then we have yellow, which is 9. Okay, so this is 0. So this is about the variational autoencoders. So the idea is that you are basically creating, so you can either use the encoder or decoder for the problem that you want. So you can see that we have basically reduced the entire image. So we have reduced the entire image into two numbers, right? So if ever you want to represent an image with a single number, what will you do? You will simply take mean, right? Or you can take a standard deviation. You can do maybe what you want. But in the framework of an variational autoencoder, these two numbers that you get from the encoder are better representation of that image, even better than the standard statistics that you will use. Okay, so that's the beauty of autoencoders and variational autoencoders, and it has been shown in multiple studies like these that how useful autoencoders are for the different applications. So this is the original paper, I think, Momita Saha et al. Autoencoder based identification of predictors of Indian monsoon. So her entire PhD is on this topic. You can see her papers, and there was a nice schematic here. So this is what she has done. So these are the input climate parameters. This is the input layer, and this is the output layer, right? Which is input and output are same, and these are the latent representation. So she has just used three-layer autoencoder, one input, one output, and one hidden layer. And this is the latent space predictors is something that she is using. So the input climate data, you do data pre-processing, anomaly data preparation, normalize the data, and after that you basically identify the climate tick predictor using autoencoder. So you have this latent representation. So from the latent representation, you basically you do the knowledge discovery, so physical interpretation of identified predictors, and then you do the prediction. So you make the nonlinear models and you do the forecast. So this paper came in 2016. You can see the plots, So she basically does for different predictors. So this is for sea surface temperature. This is for air temperature, and the climate variable corresponding to same colored geographic representation. Regions combined to represent a monsoon predictor, and different colors in the same region represent participation of that region in all those monsoon predictors. So with the sea level pressure, so here you can see using the autoencoder based latent predictors, then she is building some kind of simplified model to predict this seasonal to build a seasonal rainfall prediction algorithm, right? So this is the dark color is the actual rainfall, the light purple is the predicted rainfall. Okay, so this is as percentage of long period average, like how IMD will give the prediction. Like this year it will be a normal rainfall, or which is 95 to 105, or it is excess monsoon, or it is uh, below normal. So you can go and read this study, and if you have any questions, can ask it anytime. So